Good afternoon, professor and colleagues. Today I'm going to expose about gas and steam mixtures. One exercise again. An air conditioning system operates at a total pressure of 1 atmosphere and consists of a heating section and a humidifier that adds saturated water vapor at 100 degrees Celsius. The air enters the heating section at 10 degrees Celsius and 70% relative humidity at a rate of 35 cubic meters per minute, and leave the humidification section at 20 degrees Celsius and 60% relative humidity. Determine the temperature and relative humidity of the air as it leave the heating section, the rate of heat transfer in the heating section, and the flow of water addition to the air in the humidification section. This is a steady flow process, and thus the mass flow rate of dry air remains constant during the entire process. We get this equation, and remember to dry air and water vapor are ideal gases, and finally the kinetic and potential energy changes are negligible. The amount of moisture in the air also remains constant. It flows through the heating section, but increases in the humidifying section. The inlet and the exit states of the air are completely specified, and the total pressure is 95 kilopascal. The properties of the air at various states are determined to be remember first from table A4 that saturated pressure at 10 degrees Celsius is 1.81 kilopascal. For vapor pressure 1, we have, after replacing, remember that vapor pressure 1 equals 5.1 times saturated pressure at 10 degrees Celsius. Well, after replacing, this is dot 86 kilopascal equals PV2, and PA1, the pressure of air 1, is total pressure minus the pressure of vapor, so we get that PA1 equals 94.14 kilopascal, and the specific volume from this equation is, after replacing, 0.863 cubic meters per kilogram dry air. To find the specific humidity 1, we use the equation that we known, and after replacing, we get that specific humidity 1 is 0.00568 kilogram water per kilogram dry air, and it equals W2, the specific humidity 2. To find the enthalpy 1, remember this equation, and again after replacing, enthalpy 1 is 24.36 kilojoule per kilogram dry air. To find the pressure 3, remember from table A4 the saturated pressure at 20 degrees Celsius is this value. Again after replacing in this equation, we get that PV3 is 1.4 kilopascal. To find the specific humidity 3, again this equation, we after replacing, but for the state 3, we get that is 0.0093 kilogram water per kilogram dry air. Then to find the enthalpy 3, remember the question just before. but now applied to the N33, and after replacing we get the N33 is 43.7 kJ per kilogram dry air. To find the mass flow, remember the volume flow is given by the problem, and it's 35 cubic meters per minute. Remember this equation. After replacing, we get the mass flow is 40.6 kilogram per minute. Then, noting that heat equals work equals 0, the energy balance on the humidifying section gives. For this, remember that kinetic and potential energy changes are negligible. Remember the condition. The result is an equation in which two summations are equal. After replacing, remember this equation this we get the enthalpy 2 equals to enthalpy 3 minus enthalpy of water times this relation of mass flow. But we need this relation of mass flow, and this is gonna be calculated from the water mass balance on the humidifying section. As you can see, this relation, this division is the difference between specific humidity 3 and specific humidity 2. Finally, we've just calculate these values, and after replacing, but remember that enthalpy at 100 degrees Celsius is 2675.6 kJ per kilogram. Again, after replacing, enthalpy 2 equals to 34 kilojoule per kilogram dry air. Thus, at the exit of the heating section, we have the specific humidity is 0.00568 kilogram water dry air, and enthalpy 2 equals 34 kilojoule per kilogram dry air, which completely fixes the state. The temperature of air at the exit of the heating section is determined from the definition of enthalpy. Again, this equation, but we need an equation for temperature 2, only for temperature 2. That's why, remember, the enthalpy of water vapor in air can be taken as equivalent to the enthalpy of saturated vapor at the same temperature. That is this approximation. And after replacing in the equation of enthalpy 2, we got an equation only for the variable temperature 2, and after replacing, we got the temperature 2 is 19.5 degrees Celsius. And we need to approximate the value of saturated pressure at 19.5 degrees Celsius, because there is no the exact value in the table A4. After interpolating, we get the saturated pressure at 19.5 degrees Celsius equals 2.2677 kilopascal. And the relative humidity at this state is phi2. Remember the equation just for phi2. After replacing, we get that phi2 relative humidity is 37.9%, and the rate of heat transfer to the air in the heating section becomes this equation, and after replacing we get that this is 391 kilojoule per minute. And finally, the amount of water added to the air in the humidifying section is determined from the conservation of mass equation of water in the humidifying section. This equation we have just calculated before. Here, just replacing, we get the mw dot is dot 147 kilojoule per kilogram, and that's all. Thanks.